Let's go.
All right, let me share my screen.
Yes, yes, yes. So, hello everyone. Please welcome to this lecture. And this is our psych with Professor Marcel. And here we go, Marcel.
All right, so good afternoon, everyone, and welcome once again to our lecture series. My name is Mira Kuchibuze Marcel, and I'm affiliated with the Pan-African Citizen Science eLab. So you can check the website to investigate the kind of research we do. So in today, we are going to be treating binary stars and multiple star systems. So from the table of content, I'm going to be introducing double stars and binary stars. Many people, interchange the two. They think they are the same. They are not literally the same. So I'm going to be talking about the two. I'm going to be introducing them. Then after that, after clarifying the difference between the two, I'll talk about types of binary stars. Then I'll talk about a kind of a classification of binary stars based on size and distance. Then I'll talk about the Coronia Borealis binary star system that is expected to go nova any moment from now. I'll talk about our own observation at Pascal Lab on it. Then after that, I'll talk about the importance of binary stars. Then I'll end it with multiple stars. So what are double stars? Let me introduce what are double stars. Double stars is a pair of stars that appear close to each other in the sky. So here are two individuals observing a double star. But it is very tricky, okay? Because if you see two stars that are arranged in that form, two things are involved. Two things are involved. The first is either the stars have no relationship. They are just a chance alignment of stars in the night sky. So here is an observer looking at the two stars. As this observer is looking at these two stars, he might see this, okay? But in reality, the two stars are not close to each other, okay? Physically, they are not related. So the light rays from this star is entering his eyes, or telescope, this star is entering his eyes. So he double stars. For instance, another instance, they might actually be coming from the same part of the sky. There may be exactly what is happening here. So we call that name. So generic or investigation is going to show you if it is a binary star.
Marcel.
Star or not a binary star. So once you see verification, we can confirm if it is a binary in our lab. Us? Yeah. Yes, I can hear you.
You are logging. Go, go, gone because connection to the should not be
They are
stable.
not in orbit. They are not in. Yes, you are trying to communicate. Hello,
Okay.
Danny.
Yes.
Should I continue?
Go. Now it
Okay.
works. Now it works.
Okay. Okay. So in in the optical double stars, this is an example. The one that has no relationship. So these stars are not bound by their mutual gravity. So they are not orbiting each other. So they are just a mere chance alignment of stars in the sky. So we call that optical double stars. Then we have binary stars. Binary stars are bound by their mutual gravity and they orbit about each other. Okay, so that's exactly. So call that binary stars and optical double stars. Now, 85% of all the stars in the night sky have a companion. Okay, they have a companion. It could be a companion of 2 or 3, but they have a companion, 85%. So that's a ton of stars. So it means they are pretty much common in the universe, in the Milky Way galaxy. Binary stars are very much common in the Milky Way galaxy. But unfortunately, our sun is not a binary star system. It is not in the, presently it is not in any binary system. But we believe maybe in the past, it evolved, it formed, it has a companion when it formed. But either it tossed the companion away or the companion tossed it away, okay? So the sun, as of today, is a lone star, okay? So it is among the 15% of the stars in our Milky Way galaxies that are lone stars. They're just existing on their own. So, like I said before, we carry out research on double stars. We investigate if they are binary stars or not. So this is an observation made by one of our citizen scientists. His name is Elijah. He used the 0.4 Large Comes Observatory located at Cerro Tololo facility in Chile to observe this. So this is kind of named the BIA. They have WDS, some numbers, okay? This is just how they are named. Now, one thing I want to point out here is that if you have a double star system, most of the times, one of the stars is brighter than the other one. So the brighter one, we call it the primary star, and the fainter one, we call it the secondary star, okay? So that is just it. So now I have been able to clarify the difference between binary stars and double stars. Like I said, double stars is just the generic term, while binary is specific for stars that are bound by gravity. So so now let me introduce binary stars. A binary star is a system of two stars that are gravitationally bound to and in orbit around each other. Okay, they are gravitationally bound and in orbit around each other. So we have types. We have about 4 types of binary stars. We have what we call the visual binary stars. And secondly, we have what we call the spectroscopic binary stars. Then we have eclipsing binary stars and astrometric binary stars. I'm going to explain each of them and what they mean. So in the visual binary stars, so these are binary stars that are far enough apart that they can be seen as separate stars through our telescope. So if you look at the background of this slide here, you see an artistic depiction of a visual binary stars. So if you're observing them with your telescope, you can literally see them as separate stars, okay? They are resolvable through a telescope, okay? So we call that visual binary stars. Now, in our research of double stars or binary stars, We use several data, which includes the parallax. Parallax simply means the distances of these of the individual stars from Earth. Okay, we use it to know if they are close to each other. Okay, so if after investigation we see they are close to each other, we can know that yes, they are visual binary stars. In fact, they are binary stars and they are gravitationally bound. So in describing their distances apart, we have close visual binaries. Their distance apart is between 10 to 50 astronomical units. Then we have moderately separated visual binaries, and their distance range from 50 to 500 astronomical units. And these are the most common visual binary stars. Then we have widely separated visual binaries. They range from 500 astronomical units to about 10,000 astronomical units. Now, the farther apart they are, the longer their periods. For close visual binaries, their period are classified as short period. Their period range from 10 to 20 years. So it means that it takes 10 to 20 years for each of the individual stars to make one complete revolution around each other. Then we have moderate periods corresponding to moderately separated visual binaries. The period is between 50 to 200 years. And we have long periods that correspond to widely separated visual binaries. So they range in hundreds to thousands. So examples of these visual binary stars are Sirius. Sirius is the brightest star in the night sky. It is actually a blue star. It's a very massive star, but it has a companion star, which is a white dwarf. So this is the optical spectrum of the two systems, okay? So this is the white dwarf. It is very dim in the optical spectrum. So, but if you use UV rays, you see the brightness of this one is going to shoot out. This white dwarf is pretty bright in the UV rays. So don't mind this picture anyway. But the Sirius that we see at night, the brightest star at night, is actually visual binary system. It's a binary system that is also visual binaries. So other examples of these kind of systems are Alpha Centauri, the closest system, the closest solar system that is closer to our sun. So that is all about visual binaries. So just like I said in visual binaries, they are far enough apart that we can detect them. We can resolve them using our telescope. Now, there are ones you cannot resolve using the telescope, okay? So these are spectroscopic binary stars. So these binary stars are so close to each other that they cannot be resolved through a telescope, okay? So they are detected through what we call Doppler effect. So here you have two stars. So as it is coming closer to you, it is blue shifted, and as it's moving away, it is red shifted. Okay, you cannot detect this using a normal telescope. You have to mount a spectrograph to that telescope to be able to detect this, because these two stars are very close to each other that you cannot readily resolve them. So we call these spectroscopic binary stars. Now we have what we call eclipsing binary stars. Eclipsing binary stars they can be visual binary stars, or they can even be spectroscopic binary stars. They can be both. But in this one, an eclipsing binary star is a binary star system in which the orbital plane of the two stars, let me remove this so that I can see my slide very well. So an eclipsing binary star is a binary star system in which the orbital plane of the two stars lies so nearly in the line of sight of the observer that the components undergo mutual eclipses. So here you see the two stars orbiting each other. This one goes behind it. This one, it eclipses it. You can't see it at the moment. The other time, it comes out again. Here, it creates a light curve. So when the smaller one goes behind, this huge light curve is created. Once the bigger one goes behind, this small light curve is created. So that is how we that is how to know visual binaries. They're always causing deep in their light curve. Now, these visual binaries are very important in astronomy because we can use them to determine the sizes of these double stars. We can use it to also measure the masses just from this light curve, okay? We can also use it to determine the rotation rate of the binary system, the temperatures, the sizes and shapes of the orbit, and the distance to the star system, just from this light curve alone. So eclipsing binaries are very important. So, not all the stars are eclipsing binaries, okay? This is just the ones that are eclipsing with respect to our line of sight. So we have astrometric binary stars. Astrometric binary stars are relatively nearby stars which can be seen to wobble around a point in space. So these stars, they wobble. Look at it here. They wobble. Okay, all the stars wobble. All the stars that have a companion wobble. Okay, they move. Okay, now they wobble about a center of mass. But if you look, you won't be able to see the companion star. The companion star is invisible, and that companion star could be a black hole. I know black holes do not give out light, so we can't see them. So we only see the visible one, and it's always wobbling. It's always wobbling. So we call that as astrometric binaries. Now, other than the types of, so have what we call also size and distance of the star. So what is the Roche lobe? The Roche lobe is the region around the star in a binary system within which star, so you look at this star here, any material from that held by the gravity of that star. So this is the Roche lobe. So this particle here is bound here. So even if we have the presence of another star here, it's going to be taken out because it is outside of the idea of Roche lobe. Now, bringing the Roche lobe concept to our scope of our sun. So even if you have a companion star, they are not going to be taken away. Also, the moon and all the artificial satellites around the Earth are within the Roche lobe of the Earth. So they're not likely going to be taken away. Now, based on this classification, we have detached binaries, we have semi-detached binaries, and we have contact binaries. So in the detached binaries, so the detached binaries are binary stars where each component is within its Roche lobe. So you have these stars, so they are within their Roche lobes. And these are the most common classes. So you see them, they're not stealing any material from each other. They are just okay. They are just okay. So we have semi-detached binaries. This is where one of the components fills the binary star Roche lobes and the other does not. So this one, it could be a star that is moving away from the main sequence stage. So it begins to expand past its Roche lobe. So once it surpasses its Roche lobe, materials will be taken away from it to this other star. So here's an example of such system. So we've seen that before. Examples are black hole binaries, neutron star binaries, and the white dwarf binaries. So you have this blue giant star. It has so much inflated that some materials are being taken away from it. So we have the contact binaries. This is the case where the two stars have so much inflated that they have surpassed each other's Roche laws. So they blew up like this. So we call that the contact binaries. So now let me talk about the the Coronia Borealis, also called the Blaze Star. So this star is expected to go nova anytime from now. Okay. Now it is a recurrent novae, and novae are called cataclysmic variables. When I was talking about white dwarfs, I talked about that. So here is how they work. I want to just do a little revision on cataclysmic variable stars. So now you have a white dwarf and you have a red giant star. Okay, they are close to each other. So now if you draw a line, there will be a point along that line where the gravity of this one cancels this. Okay, so that is called the inner Lagrangian point. So if you're at that point, you will never feel any force. Now, if the two systems are closer to each other as expected, this inner Lagrangian point is going to be situated right inside this star. So now these materials that are outer here will be drawn to the star. There will be a resultant force towards here. But it is not going to just fall like that because the system is moving. So it is going to spiral around the white dwarf and spiral towards it and falling. Now, as they are falling in, they are taking the potential gravitational potential energy of the white dwarf and converting to their kinetic energy. So at the point they land on the surface of the white dwarf, they are landing at 17% the speed of light. So that is a lot of energy. So if you can convert that to energy, the kinetic energy, so that is a lot of heat generated. Now this heat is going to soar up. This heat is going to increase until 10 million Kelvin. So that is the temperature required to trigger hydrogen fusion. So, and that is what we call a nova. So there will be an explosion. So that explosion is going to disrupt this accretion disk. So after that, everything is going to settle back and the process repeats itself. So we call that cataclysmic variable, or we call that a nova. Now, the blaze star that we're talking about is about 3,000 light years away from Earth. It has experienced two eruptions in the past, in 1866 and in 1946. Now, it is expected to erupt again this August or September. So we are waiting for it. All the astronomers are observing it. So even here at Pascala, we are also observing it, and here are some of our observations. When we observe the system, we discover that the system, we did not see the other companion star, and the reason is because it is a spectroscopic binary star. So it is not possible to detect the companion star with our equipment. So what we're interested in now is to see it explode, because once it explodes, it is going to increase in brightness, and everybody is going to see it right in the night sky. So importance of binary stars. So it is important in determining the masses. Okay, masses of stars are best determined if they are in companion. So we can use Kepler's laws to determine the masses of binary star system using the Kepler third law. So once you know the period is easy to determine, the semi-major axis is also easy to determine. Other ones are the constants. So from there you can detect and measure the masses. So they're also very important in understanding star evolution in terms of mass transfer, novae, and type 1 supernovae. So they're also very important in understanding X-ray binaries and gravitational waves. So binary systems of black holes or white dwarf or neutron stars generate gravitational waves when they merge. We have treated that in the past. So multiple star systems consist 3 or more stars gravitationally bound to each other. So we have triple systems, we have quadruple systems, we have higher order systems. So I'm going to use a simulation to explain them. So here is the sun. Okay, it has only one star and it has this planet around it. Now observe other systems. Here you have 2 stars orbiting about the center of mass, but their planets are orbiting about their mutual center of mass. So their planets are not perceiving them as 2 separate entities, but the same entity that have the same center of mass. So we have, there's a mistake there. So here we have 2 double star systems, one with a planet that is trapped within its Roche lobe. So we have the same system, they are more advanced. Here you have 2 double star systems, but one of them has multiple planets. All of them are trapped within the star's Roche lobe. So we have 2 stars here with 1 planet. The planet is orbiting about their center of mass. The center of mass is somewhere here. So it is responding to that center of mass. So here you have 3 star systems. I hope you can see it. You have 3 star systems. Let me move this to this side. We have 3 star systems. Okay. So this is the arrangement of 3 star system with a planet. Okay. So these have a mutual center of mass, and the center of mass of these 2 is interacting with the center of mass of this, and that is why I have this yellow line. So we have the Centauri, Alpha Centauri system. This is the arrangement. This is Alpha Centauri A and B, and this is Proxima Centauri, another star system orbiting around them. So this is the arrangement of the star system, the Alpha Centauri. So we have 4 star system. This is the arrangement. So as the number of stars increases, it becomes more and more complicated. So this is called the Mesa star system. So we have Kepler-64, so 4 star systems. They have 1 planet. I've explained this arrangement before. So we have 5 star systems. Beta Capricorni. Okay. Then this is 5 star system, 3 stars here, and here are 2 stars. Then we have 6 star system. This is where things become very, very crazy. Star systems that are 6 in number are not usually very stable. Over a very short period of time, they tend to disintegrate. So then we have 7, we have 8, we have more and more arrangements. Now, like I said, as the number of stars increases, you have n body star systems. Now, a question that might come into your mind is, do multiple star systems tend to becoming star clusters? Okay, maybe you have a prior knowledge of what a star cluster is. Do they tend to become star clusters? And the question, I will not answer it now until I treat star clusters. So after treating star clusters, I'm going to come back and answer these questions. So I also say the difference between n-body star systems and star clusters. So that will bring me to the end of my lecture. It's quite a very short lecture. So you have any question, you can ask me. For any